Okay, we are at the very interesting territory now because we'll talk about pointers, smart pointers, how smart it could be. Yeah, so that's what we gotta do, and yeah, I don't know whether I can do all of them in one go because there are six of them, but we'll try. We'll try because today I have some meetings and I have been spending all day creating the Discord board, thing contributing. So yeah, I've been very busy, and so yeah, I don't know how much we can go through. I really want to finish them before Saturday, but I don't think I have time. So we'll go as far as we can, and then we'll come back when I'm back. So yeah, right. So smart pointers, pointers, of course. Who have been through so those who have learned something like C++ are not not you know yeah, pointer may give you a nightmare. It's like there's something that I have learned a lot when I was in school, that this is something that a lot of students really hate, is the pointer. We all found this like crazy and difficult, but how can we make it easier in Rust? So let's have a look. Pointer is a general concept of variable that contained and addressed in memory. So pointer is basically storing in an address. This address refer to a point at some other data. The most common kind of pointer in Rust is a reference, which you learn about in chapter 4. So in Rust, we just use the n symbol, so that's the reference, and that's actually the pointer pointing to that thing. And borrow the value they pointed to. They don't have any special capability other than referring to data and have no overhead. Smart pointers. Ooh, on the other hand, a data structure that act like a pointer but also have additional metadata and capabilities. This concept of smart pointer aren't unique to Rust. They originated in C++. So, and exist in other languages as well. Rust has a variety of smart pointers defined in the standard library that provide functionalities beyond that provided by references. Okay, so we haven't used those, so we'll have a look. To explore the general concept, we'll look at a couple of different examples of smart pointers, including a reference count smart pointer type. This pointer enables you to allow data to have multiple owners. Ooh. By keeping track of the number of owners, and when no owners remain, clean up the data. Ooh. Okay. I thought that Rust is basically one ownership is like the golden rule, but actually by using smart pointers you can go around that rule. That would go back to that kind of normal territory that you just have your different reference, so there will be different owners, and then at the end there's no owners, and clean up the data. So that's normally how garbage collecting work. Rust, with its concept of ownership and borrowing, has an additional difference between reference and smart pointers. While reference only borrow data, in many cases smart pointers own the data they point to. Though we didn't call them as such at the time, we already encountered a few smart pointers in this book. Ooh, including strings and vectee. In chapter 8, both these type count as smart pointers because they own some memory and allow you to manipulate it. They also have metadata and extra capability of guarantees. String, for example, stores this capacity as metadata and has extra ability to ensure data will always be valid UTF-8. Smart pointers are usually implemented using structs. Unlike an ordinary struct, smart pointers implement the deref and drop traits, because you have to dereference it and there's nothing referencing it, you have to drop. The deref trait allows an instance of smart pointers struct to behave like a reference, so you can write your own code to work with either reference or smart pointers. The drop trait allow you to customize the code that is run when the instance of smart pointers go out of scope. This chapter will discuss both traits and demonstrate why they are important to smart pointers. Given that the smart pointers pattern is a general design pattern used frequently in Rust, this chapter won't cover every existing smart pointers. Many libraries have their own smart pointers, and you can even write your own. We will cover the most common smart pointers in the standard library. Interesting. So, box for allocating values to the heap. RC is a reference counting type that enable multiple ownership, and ref mutable access through ref cell, a type that enforce the borrowing rules at runtime instead of compile times. Okay. In addition, we will cover the interior mutability pattern where an immutable type exposes an API for muting an interior value. So yeah, now it's going to deeper territory, and you can change the rules that we have learned. We'll also discuss reference cycles, how they can leak memory, and how to prevent them. So yeah, this is more advanced topic because now we are doing something considering more dangerous. Yeah. Okay, let's have a look. Using box T to point to data on the heap. The most straightforward smart pointer is a box, which type is written as box type. So box allow you to store data on the heap rather than the stack. What remains on the stack is the pointer to the heap data. Refer to chapter 4 to reveal the difference between the stack and the heap. The heap is just like a free style, free space to use to store things. Stack, you have to store things in order. Boxes don't have performance overhead other than storing the data on the heap instead of on the stack, but they don't have many extra capability either. You use them most often to this situation. When you have a type whose size can be known at compile time, and you want to use the value of that type in a context that require an exact size. So when you compile, you don't know the size, but you want to use, so there will be somehow you get a value somewhere when you run the code, and then you want to that type in a context that require an exact size. Yeah, so but you know the type of it, and you want to have the exact size of that type. Can I have an example? I don't quite get like what this sentence means. Okay, the second one, when you have a large amount of data, you want to transfer ownership, but ensure the data won't be copied when you do so. Yeah, that makes sense. When you want to own the value, and you care only that it's a type that implement a particular trait rather than being of specific type. So yeah, so then you don't know how much space you're using. You just know that there's a particular trait, but then you don't know exactly the type, so you don't know how big it is. So I guess the first one is the opposite. It's like you don't know you have a type, and the size doesn't know. Like for example, or the maximum, let's say maximum integer type, but then no, that's not a good example. Something that the size you don't know at compile time, but you want to have that exact size in the runtime. We'll demonstrate the first situation. Oh, there's a demonstration. Good. Recursive type with boxes selection. In the second case, transfer ownership of a large amount of data can take a long time because data is copied around the stack. To improve performance, we can store the large amount of data on the heap in a box. Then only a small amount of pointed data is copied around. Our data reference stays in one place. The third case is known as trait object. We've talked about that a little bit before. So you apply that again in chapter 17. So store data on the heap. Now how do we do that? Before we discuss the heap storage use case, we'll cover the syntax and how to interact with value stored within it. So for example, we have now box new 5 to store a i32 value on the heap. So define a variable b to have a value of a box that points to the value 5. So this is, yeah, of course, i32, because 5 is a i32, which is allocated on the heap. This program will print b equals to 5. In this case, you can access the data in the box, similar to how you would if this data were on the stack. So it feels the same, but the difference is that this is stored in the heap instead. Just like any owned value, when a box goes out of scope, b does at the end of main will be deallocated. This deallocation happens both for the box, which store on the stack, and the data it points to, which store in the heap. Put a single value on the heap isn't very useful, so you won't use box by themselves in this way. Have value i32 on the stack, where they store by default is more appropriate. Of course, this is just a demonstration. Don't do that in real life. Look at a case where boxes allow us to define types that wouldn't be allowed if we don't have boxes. So this is the first case that I don't understand. Now we can see it in action, then we'll understand more. A value of recursive type can have either value of the same type as part of itself. Recursive type pose an issue because of compile time. Rust need to know how much space a type takes up. However, the nesting value of recursive type could theoretically continue infinitely. So Rust can't know how much space the value need. Because box have a known size, we can enable recursive type by inserting a box in the recursive type definition. An example of recursive type, let's explore the cons list. This is a data type commonly found in the functional programming language. The cons list type we define is straightforward except for the recursion. Therefore, the concept in this example will be useful at any time you get into more complex situation for recursive types. So it's like typing within a type. Yeah, we see that a lot actually. Like, list within a list within a list within a list within a list. The con list is a data structure that comes from the Lisp programming language that is a dialect and is made up of nested pairs. And in this Lisp version of a linked list, its name comes from cons function, short for construct functions in a Lisp that construct a new pair from its two arguments by calling cons on a pair construct of a value and another pair. So for example, this is a pseudocode which there are pair in parentheses. So each item in the cons list will have two elements, the value of the current item and the next item. The last item in the list consists only the nil without a new item. So the con list is produced by recursively calling cons function, and then a canonical name to denote the base case of recursion is nil. This is not the same as null or nil concept in chapter 6, which is invalid or absent value. So this is a very special data type that basically is a list, but it is stored nested because every time you have a pair of things, so yeah, so it's kind of like peeling a onion or something like that until you hit this NIL. The cons list is a commonly used data structure in Rust. Most of the time when you have a list of items in Rust, VecT is the better choice to use. Other more complex recursive data type are useful in various situations, but by starting with cons list in this chapter, we'll explore how Boxes lets us define a recursive type without much instructions. So yeah, I think it's more like, for example, you have like I said, I worked in Terminus before, and there's all this like network of data, and then they are linked to each other, so you can have a closed loop that would create a problem, because then like you kind of use, so it's kind of like a struct, then inside there's like one attribute that links to the other, and then it could link back to this one, then it would be an infinite loop, or it can link to a very long one, so you don't know when it ends. So so that's something I remember seeing in real life of a recursive type of data structures. So yeah, this is a more simplified case that is easier to learn when we're learning. This code won't compile. So it's a list i32 cons, and then so enum is either nil or a cons like that. This one won't compile. Because list type doesn't have a known size, which we will demonstrate. Yeah, because this is list, and list is list, and then we don't know the size. We are implementing a cons list that hold only i32 value for the purpose of this example. You can use a using generics as well, so you can store any values. But anyway, we are now focusing on the cons list. So use the list type to store the list 1, 2, 3 will look like the code in 13.5, so like this. So yeah, you have the nil and then cons, then free nil, and then cons like that. Also, it won't work for now. The first cons value holds 1, and then the other is the list value, and then that list will have another con value that holds 2, and then another list, and this list is having 3 and a list value, which is actually nil. The non-recursive variants that signal the end of the list. So this is the only non-recursive thing, because this is the end. Otherwise, it will be endless. The error shows that type has infinite size. The reason is that we define list with a variance that is recursive, because list is calling itself list, so it's recursive, and yeah, it doesn't guarantee a finite size. It holds another value of itself directly as a result, then Rust can't figure out how much space it needs to store a list value. So let's break down why we get this error, and first we look at Rust, how Rust would decide how much space it needs to store a value. So for example, we have this message enum. So how much space to allocate the message value? Rust will go through each of the variants to see each variant, which one needs the most space. So for example, quit, so we'll have a look at quit. It doesn't need much space. Move, it needs to hold 2 i32 value, and then the string, and so on and so forth. Yeah, so it would determine by like assuming that it will take the largest amount of space. Construct this will happen when Rust try to determine how much space a constructive type like the list enum will. So this is what happened. The compiler will start by looking at the cons variant, so it shows the value of i32 and a value of type list. Therefore, cons need an amount of space equal to the size of an n32 plus the size of a list. So list here, so let's look at it. So it will have 932 and then the size of a list. So what is the size of a list? So we look into list, and then it's this a size of i32 and a size of list. So what is the size of list? It's like so it will be endless. Yeah, so it's like this. Yeah, that's just what I said. Yeah, they continue indefinitely, so that's why it's infinite. So what should we do? Because Rust can't figure out how much space that we need, the compiler will give us a nasty error. In this suggestion, indirection means that instead of storing a value directly, we should change the data structure to store the value indirectly. By storing a pointer to the value instead. So yeah. Because box is a pointer, so you should change it to pointer. Rust always know how much space a box T need. A pointer size doesn't change based on the amount of data, so no matter what it is, the box size won't change because it's just an address. It's determined. It depends on your computer. That's it. This means we can put a box T inside a cons variant instead of another list. Value directly, the box T will point to the next list value that will be on the heap rather than inside the cons variant. So yeah, this will be the address, and then we would, so by, instead of directly copy the list in it, we would rather just store an address, and then this address will point to the next list. So conceptually, we still have a list created with list holding the other list, but this implementation is more like placing the item next to another rather than inside one another. Yeah, because this is actually outside. We just like know that where to go to get them. We can change the definition of list enum, and then now if you change it to this, that this will compile. So yeah, but now you have to use the box new instead of just using it, because now this is a box. The current variant needs a size of i32 plus the space to store the box pointer data. The new variant stores no value, so it needs less space than const. So we know that any list will take up the size of i32 plus a pointer size of data. By using a box, we have broken the infinite recursive chain, the curse. So the compiler can figure it out, the size. It needs to store the list value. So now it looks like this. So we just a box. That's it. This is finite size. Boxes provide only the indirection and heap allocation. They don't have other special capabilities. So it's just an address label. Like those we'll see in the other smart pointer types, they also don't have performance overhead that these special capability incur, so they can be used in cases like con list. So it doesn't really take up extra time actually, because there's no overhead. This is, yeah, look at more use case. Box type is a smart pointer because it implements the deref trait, which allow box t values to be treated like references. When box t value go out of scope, the heap data that the box is pointing to is cleaned up as well, because the drop trait. These two traits will be given more important functionality provided that by the other smart pointers type we will discuss later. Let's explore. Okay, that's cool. That's the first chapter. Wow, it takes us like almost half an hour. That's why I don't think I can do, like, I only have around an hour and then I have another meeting, so maybe we'll continue in the evening. Treating smart pointers like regular reference with deref traits. Right, because of deref is just like other pointers. Implementing the deref trait allow you to customize the behavior of the dereferencing operator star. Not to be confused with the multiplication. Yes. By implementing deref in such a way that smart pointer can treat it like a regular reference, you can write code that operates on reference and use that code with smart pointers too. So for example, string, it just feels like a pointer, acts like a pointer, but actually is a smart pointer. So let's first look at how the deref operator works with regular references. Then we'll try to define a custom type that behaves like box, and see why the dereference operator doesn't work like a reference on a newly defined type. Okay, we'll see. We'll explore how implementing the deref trait makes it possible for smart pointers to work in ways similar to reference. Then we will look at Rust deref what? Deref correction. Someone need to teach me about this word. Okay. And how it lets us work with other reference or smart pointers. There's one big difference between my box, I guess is the one that we're trying to define, type we are about to build, and the real box. Our version will not store its data on the heap. We are focusing this example on derefs. So where the data is actually stored is less important than the pointer-like behavior. So yeah, just a side note, just so you know. Okay. Right. Always feel tired when I'm reading the book. I think it would be a very good read before going to bed. Okay, drink more coffee, I guess. A regular reference is a type of pointer, and one way to think of a pointer is as an arrow to a value. This is what they teach me in school when I learn C. They're like, reference is a pointer, like which is an arrow pointing to another value. Store somewhere else. We create a reference to I32 value and then use the dereference operator to follow the reference to value. So x is 5 and then y is actually the reference of x. So 5 is x, and then if we dereference y, which is getting what this is, so y itself, if you just call y itself, is actually an address which points to x. So if we dereference it, which is like going to fetch whatever x is, and then there's 5. Yeah, so if we want to n is reference, then star is dereference. That's what it is, just fetching the value. Think of it. For the reference to the value, hence the reference. So the pointer can compare the actual value. And yeah, it's 5. Yeah, if you try to do that, then it's wrong because y is not a I32 value, is a reference to that. Yeah. Then using box like a reference, so now we have x is 5 and then y is box new x. So now we can also do this to get x, which is 5. So this is y is pointer like, because it can also be dereferenced with the box value. So defining our own smart pointer. So how does it work? So let's build a smart pointer similar to box type, provided a standard library to experience how smart pointer have difference, how it works differently from the reference by default. Then we'll look at how to add the ability to use the reference operator. So box type is ultimately defined as a triple struct with one element. So yeah, this is basically the same, but it's just called myBox. Define a new function to match the new function definition. Yeah, so this is impra myBox. So new, we also have new for myBox, and they will create a new myBox struct which has only the value. We define a struct named myBox and then declare a generic parameter t because we want our type to hold any value. I mean like any value with any type, hold values of any type. The myBox type is a triple struct with only one element of type t. The myBox new function will take one parameter which is of type t, which is the value, and then return myBox instance that holds that value that got passed in. Let's try adding main function and then change it to use myBox instead of box. So this time we call myBox instead. It won't compile because Rust doesn't know how to dereference because we don't have the star. We can't dereference it, so it's now won't compile. Our myBox type can be dereferenced. Yes. So we need the deref trait. Treating a type like a reference by implementing a deref trait. To implement a trait, we need to provide implementation for the trait requires method. So the deref trait provided by the standard library requires us to implement one method called deref that borrows self and return a reference to the inner data. So for example, we want to use deref, so we would define deref for myBox type target equals to t, and then we would write this deref function. So it would take the reference of self and then it will return so self.target will return target t, the target type, the target type which is t type, and then it's self.0. So this is the first element, right? So this is just the thing that we have been holding all the time. Yeah, we'll give it back. That's deref. The type target T syntax define associate type for deref trait to use. So yeah, it's just defining target is T because we're using here. Associate types are a slightly different way of declaring a generic parameter, but you don't need to worry about them for now. We'll talk about that in chapter 19. We'll fill in the body with and self.0, so deref return a reference to the value we want to access with the star operator. Yeah, because like if it's a triple struct, then you just like 0, 1, 2, 3, 4, right? Let's .0 access that value. The main function we call star, and then now it will compile because it will know the deref, and then it will do this. Right. Without the deref trait, the compiler can only reference the n reference, only dereference n references. The deref method gives the compiler the ability to check a value of any type that implement the deref, and then it will call the deref method to get a n reference that know how to deref. When we entered star y in list behind the scene, Rust actually called this code. So it will call the deref and then substitute the star operator with a call to deref method, and then a plain dereference, so we don't have to think about whether or not we need to call the deref method. The Rust feature let us write code that function identical whether we have a regular reference or a type that implement deref. So if that's not, then it would just run the star. The reason the deref method returns a reference to a value and that plain dereference outside. Yeah, we still need this because deref will return a reference. This one is n self target, so it's still a reference. Yeah, so that's why we need the star. Here. Still necessary to is to do with the ownership system. If deref method return the value directly instead of the reference to the value will be moved out of self. We don't want to take ownership of the inner value inside mybox T. So the ownership still stays in mybox T because when we call deref, everything is just reference. This is just referencing cell, and this is just referencing the value, and this is just a reference. So we are not passing the ownership of it outside. So it still stay in my box. Ownership, yeah. So note that the star operator. Sorry, I'm very tired. Note that the star operator is replaced with a call to the deref method and then a call to the star operator just once. Each time we use a star in our code, because the substitute of the star operator does not recurs indefinitely, we end up with the data of type i32, which match the 5. Yeah, so this star operator is only replaced once. So this star won't be replaced again, otherwise it's indefinite again. Yeah, so it will just replace once the star. So this one won't be replaced. This one will be. Implement deref creations. Someone teach me that word, please. With functions and methods. So what does it do? It converts a reference to a type that implements the deref trait into a reference to another type. For example, deref can convert n string to n star because string implement the deref trait such that it returns an n star and perform on an argument to functions and methods. Work only on types that implement the deref traits. Okay? Happens automatically when we pass a reference to a particular type's value as an argument to a function or method that doesn't match the parameter's type. A sequence of calls to deref method convert the type we provide into the type the parameter leads. So actually it will sometimes automatically work because when we pass as a parameter, the deref will be called automatically. Deref creation was added to Rust, so the program writing function and method calls don't need to add as many explicit reference and dereference with n and star. The deref creation feature also let us write more code that we can work for either reference or smart pointers. So, for example, we have the myBox type we defined before. So the deref that we added. So the definition of a function. So this is hello, and the name is n string like that. We call the hello function with a string slice as an argument, such as hello Rust, for example. Deref creation make it possible to call hello with a reference to a value of type myBox string. For example, like this. So it's a string. So we can just reference m. So now, when we call the hello function with argument nm, which is a reference to this, because we implement the deref trait on myBox, Rust can turn myBox string into just string by calling deref. The standard library provides an implementation of deref on string. So again, string will also be deref, and then it will become a string slice of Rust. And this is from the API documentation of deref. Rust code deref again to turn a string into an n star, which matches hello function definition. So this will work because, well, first of all, myBox will be deref to string, and then this string will be deref to n string like this, and then it will work. So yeah, that's a convenience. If Rust doesn't implement the deref, we would have to write the code. Yeah, so what we have to do is to do the shenanigans. So first of all, okay, so I dereference m, so it will be give me myBox, and then I deref myBox, which will give me the string, and then the string I will take the whole thing as a slice, and then now I can put it in hello, which is a nightmare. Yeah, this is what it says. And then n, and so this will become this string here will become here, and I can n and then do the slicing, string slice. The deref traits is defined for types involved. Rust will analyze the types and use derefs as many times as necessary to get the reference to match the parameter's type. The number of times that deref needs to be inserted is resolved at compile time, so there's no runtime overhead as well. Cool, nice, very cool feature. A bit difficult. It got very difficult to pronounce name, but it's really cool. So how it interacts with mutability, another question. Similar to how you use a deref trait to override the star operator on immutable reference, you can now use deref mute trait to override the star operator. Reference type and trait implementation in this case is nt to nu when t derefs target is u, then it will become u because it will be called this, right? Deref. Mute t to mute u when you have a deref mute. So this time you have to have mute. But yeah, just mute and it will do similar thing. Mute t to nu when you only have deref. So this time even if you call it mutable, but because you don't have deref mute, so this won't be mutable. The first two cases are the same as each other, except the second one you have to implement mutability. The first case data, if you have nt and t implemented deref to sometimes you would get a nu transparently. The second case data, the same deref coercion happens for mutable references. The third case is trickier. Rust will also do that with a mutable reference, but to an immutable one. But the reverse is not possible, which means that immutable reference will never become mutable. Because of these borrowing rules, you will have a mutable reference that the mutable reference must be the only reference to that data. Yeah. Because like if it suddenly become mutable, then like it will easily break the rules because we can only have one mutable reference, right? Converting one mutable reference to an immutable reference will never break the borrowing rule because it would just have less mutable reference. Converting an immutable reference to a mutable reference would require the initial immutable reference is the only one. So, yeah, but it's not guaranteed, so Rust can't do that. So, yeah. No. So, only from mutable to immutable. Immutable to mutable, risky. Don't do that. Right. Next. Yeah, let's finish this chapter and then maybe I would continue in the evening. Running code on a cleanup with the drop trait. So the second trait importance to the smart pointer is drop, which lets you customize what happens when a value is about to go out of scope. You can provide an implementation for the drop trait on any type, and that code can be used to release resources like files or network connections, not just memories. Yeah. It will get called when it goes out of scope. We're introducing drop in the context of smart pointers because the functionality of drop trait is most always used when implementing a smart pointers. For example, when we have box is dropped, then it will delocate the space on the heap where things are stored. So in some languages, for some types, programmers call code to free memory or resources every time they finish using an instance for that type. That's your responsibility to collect garbage. Very scary. Huge responsibility. Example includes file handles, sockets, or locks. If they forgot, the system may become overloaded and crash. In Rust, you can specify that a particular bit of code be run whenever a value goes out of scope. And the compiler will insert this code automatically. As a result, you don't need to be careful about placing cleanup codes. Yeah, because if you put in drop when the thing go out of scope, then that code will be there automatically because it added when it's got compiled, so it will always be there. In a program that an instance of particular type is finished with, you still don't leak resources. So yeah, that's very important. You specify the code to run when a value goes out of scope by implementing the drop trait. The drop trait requires you to implement one method named drop that takes a mutable reference to self. To see when Rust code drop, let's implement drop with printline statement for now. So it would just printline. Custom smart pointer struct. Only custom functionality is that it will print dropping custom smart pointer when the instance goes off scope to show when Rust run the drop function. Yeah, so we can see when it run the function. So this is the only thing it does. When it drops, they just print out something. So we create the pointer. The data is my stuff, and then we create another pointer. There's data is another stuff, and then we'll print line. Let's create it. So when do we see that line? It will give us a hint of when it got dropped. The drop trait is included in the prelude, so we don't need to bring it into scope. We implement the drop trait on custom smart pointers and provide an implementation for the drop method that calls the print line. The body of the drop function is where you would place any logic that you want to run when an instance go out of scope, and you have to destroy that. we are printing some text here to demonstrate when it got called. In main, we create two instances and then print out it's been created. And then at the end of main, you'll go out of scope. So when we call it, we should set, so it will create the two thing, and they will set it got created, and then they will get dropped. So they will at the end will be dropped here. Rust will automatically code drop for us when our instance went out of scope. Calling the code we specified, variables are dropped in the reverse order of their creation. So you see that we have created my stuff and other stuff, so we will queue other stuff first before my stuff. D was dropped before C, that's why. The example purpose to give you a visual guide of how drop method works. Usually you would specify the cleanup codes that you your type needs to run rather than printing a message. Yeah, this is just a demonstration. Dropping a value early with standard mem drop. Unfortunately, it's not straightforward. To disable the automatic drop functionality, disabling drop isn't usually necessary. The whole point of the drop trait is that it's taken care of automatically, so don't mess with it. But occasionally, however, you may want to clean up a value early to save space. One example is when you're using smart pointers that manages locks, you may want to enforce the drop method that release the lock so that other code in the same scope can acquire the lock. Rust doesn't let you call the drop trace drop method manually. Instead, you have to call the standard mem drop function provided by a standard library if you want to force a value to be dropped before the end of the scope. If we try to call the drop method manually, then we'll get an error from the compiler. So for example, here we create a smart pointer, and then we want to call the c.drop, which is the drop function that we have implemented. Then you will have an error. You can't call it directly; it's not allowed. Yeah. A destructor is an term destructor, which is general. Yeah, a destructor is an analog to a constructor. Create an instance. So the drop function in Rust is one particular destructor. So we can't call drop because Rust will automatically call drop on the value that's at the end of main. So yeah, we will free 2 times, which is again a big no-no. That we have talked about that before. We can disable the insertion automatic insertion of drop. A value go off scope. We can call the drop method explicitly. So if we want to force a value to be cleaned up early, so we have to use this. Mem, I think, is memory. So standard memory drop. It's different from a drop method in a drop trait. We call it by passing an argument value we want to force drop. The function is in the prelude, so we can modify main like this. So it's already in the prelude, so you can just call it drop like that. Yeah, so we can see we can drop it and before the end, so it's here before the end of main. You can use code specified in drop trait implement in many ways to make cleanup convenience and safe. For instance, you could use it to create your own memory allocation with the drop trait and Rust ownership system. You don't have to remember to clean up because Rust does it automatically. Just have to remember to implement the drop trait. Yeah. Right. You also don't have to worry about problems resulting from accidentally cleaned up values still in use. The ownership system that makes sure references are always valid also ensure that drop get called only once when the value is no longer being used. Now we have examined box T and some characteristics of smart pointers. Next time we will look at a few other smart pointers to find in standard libraries. So I think that's it for me. It's almost an hour. I'm tired, and hopefully we'll have some time in the evening and then we'll go through the rest of the chapter. So a chapter a day keeps the doctors away, I guess. um, yeah, so yeah, we will try to finish chapter 15 and then tomorrow chapter 16. And if we are good, we can also do chapter 17. But then the rest will be when I come back from my travel and conferences and everything. It's getting more and more busy because of all these conferences. Yeah, but then hopefully by the end of July we'll finish the book. We'll finish the wrestling exercises, and then in August we can find something fun to do. And then yeah, continue our Rust journey. It's been a long journey. Thank you so much for being with me. I'll see you later.